Hello, I am Milan Matic. I will be discussing the classic Belousov-Zhabotinsky oscillating reaction, which uses bromate and malonic acid and cerium as a catalyst. The Bezy reaction is one of the few known oscillating chemical reactions, discovered by Belousov in 1958. By mixing potassium bromate, cerium sulfate, and citric acid and diluted sulfuric acid, he found that the concentrations of cerium-4 and cerium-3 ions oscillated. Zhabotinsky later found that this oscillation would occur with any carboxylic acid possessing the general formula shown in the lower right. Essentially, oscillations occur because the system is so far from equilibrium that it is overshot, causing the color changes that characterize this family of reactions. Outlined here is a list of the chemicals and equipment necessary to replicate the following demonstration. The entire process consists of a mixture of 4 solutions. The first 3 are labeled A, B, and C, and the fourth is an indicator to make the oscillations more visual. A is a 0.23 molar solution of potassium bromate, B is a 0.31 molar malonic acid and 0.059 molar potassium bromide solution, and C is a 0.00193 molar ceric ammonium nitrate and 2.7 molar sulfuric acid solution. The indicator is ferroin solution prepared by first dissolving a small quantity of iron 2 sulfate heptahydrate and phenanthrene. This slide presents the procedure in more detail for those who wish to recreate the experiment. When attempting this demonstration, avoid chloride ion contamination, as even a small amount can interfere with the reaction mechanism. Sulfuric acid is a strong acid and a dehydrating agent, so it can cause burns. Wear gloves in a lab coat for safety and make sure spills are cleaned up with an appropriate chemical, such as sodium bicarbonate. Additionally, malonic acid is a strong irritant and bromates are flammable. Solutions A and B are mixed together in a magnetic stirrer. Normally it would now develop an amber color indicating the presence of elemental bromine. This did not happen, likely because of the undissolved potassium bromate. My thought was that it would dissolve in the mixed solution, and while this never happens completely, the oscillation still occurred. Alternatively, you could heat up the potassium bromate solution until it all dissolves and then begin mixing. Next, solutions C and ferroin are added. The mixture of the two creates a murky yellow liquid. Once it clears up, it'll turn to green and the oscillations will begin, going from green to blue to violet to red and then back to green, repeating more than 20 times. Now, each color change corresponds to a specific concentration of the ions involved. As the cerium oscillates between its reduced state cerium-3 and its oxidized state cerium-4, the iron complex is also oscillating between its reduced state iron-2 and its oxidized state iron-3. Cerium-3 is clear, cerium-4 is yellow, the iron-2 complex is red, and the iron-3 complex is blue. Knowing this in some basic color theory, deriving the relative concentration of the ions at any point is a simple procedure. This equation here represents the full reaction that is taking place. The bromate is being reduced to its ions and the malonic acid is oxidized to carbon dioxide and water. This on its own, however, does not explain the periodic changes in color, the effect of the cerium, or the role of the bromide ions that were present at the start of the demonstration. Therefore, to understand these phenomena, we have to examine the reaction mechanism. The reaction is governed by two main processes, A and B. In A, the first reaction, A net, is what occurs after solutions A and B are mixed. Once the malonic acid is added, the second reaction also occurs, and together they bring down the concentration of bromide ions. In addition, the reaction creates intermediaries for process B, and once a sufficient quantity of bromide is consumed, the rate of reaction A becomes negligible and process B dominates. For process B, the reaction B net is the overall process, initiated by Roman numeral 1 and 2. These two reactions also cause the autocatalysis of hypobromous acid, as can be seen in the fourth reaction. Also, both the cerium-4 and the elemental bromine produced by B net partially react to oxidize organic material with the formation of bromide ion. As the concentration increases, so too does the rate of A net, until it eventually overtakes B and the system is again dominated by process A. The dominant process then continues to fluctuate and results in the color changes that are observed. Two important concepts to understand when discussing the BZ reaction are dissipative structures and time translation symmetry. A dissipative structure is an organized non-equilibrium state of matter created and maintained due to dissipative processes, i.e. losing energy over time. Time translation symmetry is the term used to describe processes or phenomena in which time is not an explicit variable. For example, a particle in a gravity field does not lose energy with the passage of time, therefore it is said to have time translation symmetry. On the other hand, the BZ reaction as well as other oscillatory reactions are dissipative structures that form as a result of the breaking of this symmetry. To conclude, oscillating reactions are just a part of a larger field of research that studies far from equilibrium systems, which may help even explain the development of living organisms. In 1952, the British mathematician Alan Turing suggested a mechanism based on the processes of chemical reactions and diffusion to explain the morphology of things such as tiger stripes and the patterns on butterfly wings. He proposed that these principles could work together to produce stable, stationary patterns of concentration, called Turing structures. While today we understand biological morphogenesis is much too complicated to be explained solely by this mechanism, Turing's research is still of great interest to chemists who study far from equilibrium systems because of the intriguing implications such research entails. Thank you for listening to this presentation on the classic Belousov-Zhabotinsky reaction.